Good morning, class. At this point, you should now be able to identify when a relation is a function and also identify domain and range of a function. Now, what we want to do is to be able to evaluate functions, okay? Because what does a function really do? Okay, a function transforms an input into its corresponding output using predefined rules. Now, think of this as, again, going back to the vending machine. If I pressed E3, the vending machine will give me Cheetos. If I pressed C6, the vending machine will give me Ruffles. So the vending machine is like a function. Okay, the vending machine itself is similar to a function because it transforms the input or the letter combination, the letter number combination that I type, and give me back the snack that I want. Let's see this in a different way. So as I said here, this is the function is like a machine. See, we have this machine. You put something in, here's your input, and this is usually X, and you get something out. Usually we use the variable Y to indicate the output. Okay. Now we use function notation to denote our function, and we usually use f of x. This is how we read this. F of x. Oops. F parentheses x close parentheses means f is a function of x. It's meant to transform x into an output f of x or the variable y. Okay, so make sure we're familiar with this notation. And of course, it doesn't have to be necessarily just using the variables x and or f or the function f. Say we have the circumference function. In a circle, the circumference is like the perimeter of the circle. Okay, so like how long the perimeter of the circle is. Now, to figure out the perimeter of a circle, for example, we can use the diameter. The diameter is like the longest line segment inside the circle. So this is the diameter. And if in this machine, in this circumference machine, my input will be the diameter d. Now what I will do, the rule for this function is to multiply it by pi, and I will get circumference if the radius is d, or c of d. Okay, so our function c of d, we can derive it by multiplying the diameter by pi. So in this case, the circumference is a function of the diameter d. Okay. Now let's use other representations to evaluate functions. Now these three, this table, this mapping, and this set of ordered pairs all represent the same function. So if, for example, we're asked f of 3, we can use the table to figure out what f of 3 is. That means if I put 3 in, what am I going to get out? As you can see here, it's 9. And we can double check that with the other representations. Here at 3, if I put in 3, you see that you get 9. And in the ordered pairs, you can also see here, remember the first number is the input, the second one is the output. So if you put in 3, you're going to get 9 out. Now similarly, f of 6, if you just do the same thing, as you can see here, here's 6, and here's 6. You will see that f of 6 is equal to 36. Now let's do it differently. We are asked for what value or values of x is f of x equal to 16. In this case, we are given the output, f of x equals 16, and we need to know the input. So when is the output 16? So you can see here 16, and thus the value of x that would work there is equal to 4. So in this one, x equals 4. The second question is, for what value or values of x is f of x equal to 4? And again, you have to find the outputs that are 4, and we see them here. 4 and 4 are actually, you can use the mapping as well and see what inputs point to that output, and you can see from the table, from the mapping, and even from the ordered pairs that the x's that we are looking for are x equals 0 or 2. So that's how we evaluate functions using a table, mapping, and ordered pairs. Now let's see it again on a different representation. Let's say we have a word problem. Okay, see, a compact disc is read at 44.1 kilohertz. That means a CD player scans 44,100 samples of sound per second on a CD to produce the sound that you hear. Now the function in this one they give us, and here's another way to represent this function, through a formula. S of t is equal to 44.1 t describes this number of samples of sound, S of t in thousands, that are scanned in t seconds. Okay, so in this one, S of t, which is number of samples of sound in thousands, is a function of time t, which is in seconds. And to figure it out, all we have to do is multiply the time in seconds by 44.1. So for example, how many samples of sound are scanned after 30 seconds? All we have all they're asking there is S of 30. And that just means, what is 44.1 times, replace t by 30, times 30. So let me do that quick. So 44.1 times 30 equals 1,323. Okay, so S of 30 equals 1,323. Now remember though that S of t is in thousands. So this one really is, we have to add 3 more 0 because it's in thousands. Or actually just write the word thousands, you know what? Because otherwise it will be misleading. So thousands, or the other way to write this is, the final answer would be 1 million, because if the thousands represent uses 3 zeros, 1,323,000 samples. Okay, so a CD scans 1,323,000 samples of sound after 30 seconds. So, the second example, how many samples of sound are scanned after 2 minutes? Now in this one again, the time has to be in seconds. So what we need to do first is convert 2 minutes into seconds, and we know there are 120 seconds in 2 minutes. So what we're really looking for here is S of 120. Okay, so similarly, we do 44.1 times 120, like what we did earlier, which is equal to 5,292. Now remember, this is in thousands. So this means in 2 minutes, a CD can scan 5,292,000 samples of sound. Now in the third part, we're given something different. We are asked how long would it take the CD player to scan 1,764,000 samples of sound. Okay. Now remember, S of t gives it to us in thousands. So what we're really looking for here now is, for what t is S of t equal to in 1,764, because again the S of t gives it in thousands, so we can ignore the 3 zeros. And to solve this, we know what S of t is equal to. It's 40 more. We can go back here, 44.1 t. So we do 44.1 t equals 1764, and then we divide both sides by 44.1. And if we do that, okay, we find out that t is equal to 40 seconds. Okay, that means it takes the CD player 40 seconds to scan 1,764,000 samples of sound. Let's see, answer two more questions about this problem. Would negative numbers be in the domain of this function? That's the same as asking, would negative numbers be, could they be inputs? Okay, and we know that time cannot be negative, right? Because how can you say, like, say negative 2 seconds? And thus, the answer to this question is no. We cannot have negative numbers in the domain of this function. And last, with respect to this problem, find t so that s of t equals 882. So again, we know what s of t is. It's 44.1 times t. And that's all really we have to do. 44.1 t, set it equal to what s of t is, which is 882 in this case. Dividing both sides by 44.1 is equal to 20. So t is equal to 20. Now this one is in seconds. This means in 20 seconds, a CD can scan. Now remember, this is in thousands. 882 is in thousands. 882,000 samples of sound.